Okay, suppose that I have a constant magnetic field. And in this case, I have a magnetic field with a magnitude of 0.01 Tesla, and it's going into the paper. That's what all these X's represent. They represent the vector arrows pointing into the paper. And then I shoot a proton with some velocity v into this magnetic field. What will happen to that proton? So let's first look at the magnitude of the magnetic force on that particle. So here, if I have a particle in a magnetic field, the force is going to be QV cross B. So this is a vector cross product. We can find the magnitude of this, though, as this QV times the magnitude of B times the sine of the angle between them. And the direction will be with the right-hand rule. So in this case, my magnetic field is straight down, my velocity is straight up, the angle between those is 90 degrees, the sine of 90 is 1. So what about the direction? So here I use my right-hand rule. Okay, so and I also have this. So if this is QV and this is B, this would be the direction of the force. And so the way you find this is that the force has to be perpendicular to both QV and B. And then, so there's two, there's up or down. And then you use your right hand rule to determine which one it is. So it's like this. So let's put QV going that way. And then B, I want going down. So that means that my magnetic force is going to be to the left. Let's draw that in red. So what's the motion of this particle going to be like when it has a force pushing it to the side? Is it going to move to the side? No, it's not. It's not going to move to the side because the force, remember, the momentum principle says that F net is the change in momentum over the change in time, or mass times acceleration. So this tells you the direction the object's going to accelerate. This tells you the direction the velocity is going to change. So if the velocity is this way, a little bit later, it's still moving that way, but now it has a velocity to the side a little bit. So a little bit later, it could be right here, going this way. So at that point, what's the direction of the force? Let's redo the problem. Now the magnetic field's still down. QV is that way, and we get the magnetic force is this way. So that means that it will again change directions, and then over here it will be going this way. I'm just picking these as arbitrary. So let's redo the force calculation. Now it's like this, and now I have the force is down. And you'll see that if you follow this out and you get this circular path, and it will actually move in a circle. And we can calculate the radius of this circle. So let's calculate the magnitude of the magnetic force is constant, because since the force is perpendicular to the velocity, it doesn't change the magnitude of the velocity. It only changes the direction. And the magnetic field doesn't change. So the net force I can calculate, the magnitude of the force is just going to be QVB. And since it's moving in a circle, then we can go back to the previous chapter and say that this is the mass of the object times its acceleration, which is v squared over r. This is the acceleration of an object moving in a circle. So if I solve this for r, I get r equals m v squared over qvb. One of the v's cancel. I get m v over qb. So now if I use a mass of a proton with 1.6 times 10 to the negative 12 kilograms, the charge on a proton is 1.6 times 10 to the negative 19th. And if I use a velocity of 2.2 times 10 to the 5th meters per second, I just pick that. That gives me a radius of 0.23 meters. So it moves in a circle at a constant speed as long as it's in that magnetic field. If the magnetic field is constant, okay? But motion of an object in a constant magnetic field, a charged particle would move in a circle. What if this was an electron instead? If it was an electron, then the force would actually be in the opposite direction, because now I have QV is negative. So if I have this was before, but now QV is this way because I have a negative charge. So that would mean that I'm like this, and the force would be to the right, and it would make it move, and so it would move in a circle like this. So a positive charge will move in a circle to the left, a negative charge will move into the circle to the right. And there you have it. That's the motion of a particle in a magnetic field. It's actually important for things like a mass spectrometer. I'll talk to you physics people later, and we'll do another problem.